Welcome to our deep dive, everyone. Today we're going to be tackling Stephen Hawking's A Brief History of Time. You know, the one that seemed like everyone and their grandma had on their bookshelves back in the day. We're going to try to unpack some of its biggest ideas. Stuff like the origin of the universe, the nature of time and space, and we'll see if we can wrap our heads around some of these mind-blowing concepts.
Yeah, it's a tall order for sure. Hawking, he really takes us on a journey, and what I find most fascinating is how he uses this search for a theory of everything to tie together like centuries of discoveries. It's a story that starts way before Einstein even.
Right. He starts things off with that funny anecdote about the scientist and the old lady, the one who believes the Earth is on a giant tortoise. Turtles all the way down.
Turtles all the way down.
It really shows how our models of the universe have evolved over time.
Yeah. You know, it's a perfect way to illustrate how we went from those early geocentric models, where everything revolved around the Earth, to the more modern view, of a vast and expanding universe.
So let's talk about those early models for a sec. Ptolemy's Earth-centered model with its epicycles and difference. I mean, that was pretty complex, wasn't it?
Oh, it was. And while it did a surprisingly good job, of predicting the positions of planets and stars, it had some major flaws. Like the idea that the moon's distance from Earth could vary so much that it should appear twice as big at times. I mean, clearly something wasn't quite right there.
No, not quite right. So that's where Copernicus comes in, right? He shakes things up with his heliocentric model and putting the sun at the center of the solar system. Was that a smooth transition, or was there pushback?
Oh, definitely pushback. This was a radical shift in thinking, and it took time and more evidence for the idea to gain widespread acceptance.
Well, if the moon size didn't convince people, what did? Telescopes weren't exactly commonplace back then.
You've hit upon a key point there, observation. Galileo's observations with his telescope, those were crucial. Seeing Jupiter's moons orbiting Jupiter, not the Earth. That was a big blow to the Earth-centered view.
So that's where things really started to shift. But even with the sun at the center, there were still pieces of the puzzle missing.
Exactly. And to fill in those gaps, we need to jump ahead a few centuries to the two pillars of modern physics. So that's Einstein's general theory of relativity, which describes gravity and the large-scale structure of the universe. And then you have quantum mechanics, which governs the subatomic world.
Two theories that seem to clash at their core. One governing this vast cosmic realm, and the other delving into the unbelievably tiny world of particles. And yet, both incredibly successful in their own domains.
And that inherent conflict, that's precisely why the search for a unifying theory, a theory of quantum gravity is one of the biggest challenges in physics. It's the holy grail. It's the key to a deeper understanding of the universe.
And Hawking, he doesn't shun away from that challenge, does he? He even suggests that our scientific discoveries might actually lead to our own destruction. Talk about a sobering thought. But thankfully, he also maintains a sense of optimism, trusting in our innate curiosity to keep searching for answers.
He does. And one of the most intriguing aspects of this search, I think, is how relativity revolutionized our understanding of space and time. It completely shattered the Newtonian notion of absolute space and time. Everything's relative, isn't it?
So no more thinking of time as this universal, unchanging thing. But what exactly does that mean? How do we wrap our heads around the idea of relative time?
Well, it all comes down to the observer. Imagine you're on a train, and you're watching someone play ping pong. Okay. So for them, the ball just goes up and down, right? But for you, on the moving train, the ball is traveling a diagonal path.
Okay, I can see how motion changes the perceived path, right?
Yeah.
But how does this relate to time itself? Is it like time is moving at different speeds for different observers?
Exactly. And the kicker is that the speed of light is constant for all observers, no matter how fast they're moving. This seemingly simple fact has profound implications for our understanding of time. It means time is not independent of motion.
Whoa. Okay, this is where it starts to get mind-bending. It's like saying my clock runs at a different speed than yours if we're moving relative to each other. But how do we know that the speed of light is constant? Is there an experiment that proved that?
There is. It's called the Michelson-Morley experiment. They were actually trying to detect this mysterious ether, that physicists believe light waves travel through. But instead of finding evidence for the ether, they stumbled upon something far more profound. The speed of light is constant, regardless of the Earth's motion.
So that blew the whole ether theory out of the water, huh?
Yeah.
And led to this idea of space and time being intertwined as this four-dimensional fabric, called space-time.
Exactly. And this fabric, imagine it like a giant trampoline.
Wow.
Okay, it can be warped and curved by mass and energy. Think of a bowling ball placed on that trampoline, distorting the surface. That's similar to how mass warps space-time. And this warping, that's what we experience as gravity.
So gravity isn't a force acting at a distance, but a consequence of this curved space-time.
Precisely. That's one of Einstein's most brilliant insights. And this leads to all sorts of fascinating phenomena, like light being bent by the gravity of massive objects.
And wasn't that confirmed by that famous 1919 eclipse expedition, where they observed starlight bending around the sun?
Yeah.
Just as Einstein predicted. I mean, it even made headlines as a post-war reconciliation between Britain and Germany, right?
It did. Though, funnily enough, later analysis showed that their measurements were actually pretty inaccurate. They got lucky that their errors were about the same size as the effect they were trying to measure.
Huh. So sometimes even groundbreaking discoveries involve a bit of luck. But this warping of space-time also leads to another wild idea. Time dilation? Is that where the famous twins paradox comes in?
Yes, that's a classic thought experiment that illustrates time dilation. Imagine two twins, okay? One stays on Earth while the other travels at high speed in a spaceship. When they reunite, the traveling twin will be younger.
Wait, what? Seriously, how is that? I mean, how is that even possible? Are we talking like a few minutes difference or something more dramatic?
It depends on the speed and duration of the journey, but the difference can be significant. It's a direct consequence of the fact that the speed of light is constant. Time passes slower for the traveling twin relative to the twin who stayed on Earth.
Okay, that is just mind-blowing. Time travel, even if only a few seconds into the future, is a real thing. But before we get too lost in time warps, let's bring it back to something a little more familiar. Stars. Hawking mentions how we can learn about them even though they appear as mere points of light. How is that? I mean, how is that possible? Do we just guess?
Not at all. It's all about analyzing the light they emit. By breaking down a star's light into its different colors, we can create a spectrum, and that acts like a fingerprint, revealing its temperature and composition. It's a powerful tool for understanding the universe.
So it's like starlight carries coded messages about the star itself.
Exactly, and there's this phenomenon called the Doppler effect. You've probably experienced it with sound waves. Think about a passing ambulance siren.
Okay.
The pitch gets higher as it approaches and lower as it moves away. This happens because the sound waves are compressed or stretched, depending on the motion of the source. Light waves behave the same way.
Okay, so if a star is moving towards us, its light waves are compressed, making its light appear blue or blue shift.
Mm-hmm.
And if it's moving away, its light waves are stretched, making it look red or red shift.
Mm-hmm.
So we can actually tell if a star is moving towards or away from us just by looking at its light.
You got it. And this technique, it played a crucial role in one of the most important discoveries in cosmology, the cosmic microwave background radiation.
Ah, yes, the famous story of Penzias and Wilson accidentally discovering this faint echo of the Big Bang while they were trying to get rid of noise in their microwave antenna. They even thought bird droppings were to blame at one point.
Mm-hmm.
Talk about a cosmic aha moment. But what exactly is this cosmic microwave background radiation, and why is it so important?
Well, it's a faint glow of radiation that pervades the entire universe. Think of it as a leftover heat signature from the Big Bang. It provides incredibly strong evidence for the idea that the universe began in a hot, dense state, billions of years ago, and it completely contradicted the steady state theory, which argued for a universe that had always existed.
So thanks to some persistent static and some curious scientists, we got confirmation that the universe did have a beginning. What a game changer! But how do we know how the universe evolved after the Big Bang? What happened next?
That's where we need to look at the Friedman models, which are based on Einstein's general theory of relativity. They describe different possible scenarios for the expansion and evolution of the universe, linking the concept of curved spacetime to the fate of the cosmos.
So are we talking about a universe that keeps expanding forever, one that eventually collapses in on itself? Or something in between?
Those are all possibilities, and understanding them leads us to one of the most mind-boggling aspects of cosmology, the Big Bang singularity.
Ah, yes, the Big Bang singularity, the point where everything began, where the density and curvature of space-time become infinite, and general relativity, our best description of gravity, breaks down. Are we talking about a moment where time itself began?
That's the truly mind-bending question, isn't it? It challenges our very understanding of time as something that has always existed. And it leads us right to the edge of our current knowledge, into the realm where physics as we know it can't quite explain what happened.
It's amazing to think that the universe had a beginning, that time itself might have had a starting point. But if the Big Bang is the beginning, what came before?
That's a question that continues to fascinate and perplex scientists. Some theories, they suggest a cyclical universe, with periods of expansion and contraction. Others propose a multiverse, where our universe is just one of many. But to delve deeper into those ideas, we need to explore the other pillar of modern physics, quantum mechanics. That's where we'll pick up in our next part. Ready for a deep dive into the quantum realm?
All right, let's dive into this quantum realm you mentioned. Mm-hmm. Quantum mechanics always seemed, like this mysterious, almost magical area of physics, but is it really that different from the physics of everyday life?
It is in some ways radically different. Yeah, quantum mechanics deals with the world of the incredibly small, like atoms, particles, and the forces that govern their interactions. It's a world where our everyday intuition, it often breaks down, and things behave in ways that seem counterintuitive, even bizarre.
So what are some of these key differences that make quantum mechanics so strange? Give me an example of something that just wouldn't make sense in the normal world.
Well, one of the most fundamental concepts in quantum mechanics is wave-particle duality. It's the idea that things we normally think of as particles, like electrons, they can also behave like waves, and things we think of as waves, like light, can behave like particles.
Wait, hold on. How can something be both a particle and a wave? That doesn't make any sense. A particle is like a tiny ball. A wave is like a ripple in water. They're completely different things.
Exactly. Our everyday experience tells us that things are either one or the other. But in the quantum world, the lines they blur. It's like saying a baseball can sometimes act like a ripple in a pond, depending on how you observe it.
So is it just a matter of how we're measuring things? Does the way we look at these tiny particles somehow change their behavior?
That's a big part of it. Yeah. In quantum mechanics, the act of observation can actually influence the state of a system. One of the most famous examples is the double slit experiment.
Oh yeah, I've heard of that one. Isn't that where you shine light through two slits?
Yeah.
And you get this pattern of bright and dark bands, like waves interfering with each other. But how does that prove anything about particles behaving like waves?
Here's the mind-blowing part. You get the same interference pattern even when you fire single particles, like electrons, one at a time through the slits. It's as if each particle somehow knows about both slits and goes through both of them simultaneously, interfering with itself.
So a single electron can be in two places at once. That just seems impossible.
It does, doesn't it? It defies our classical understanding of how things should work. But numerous experiments, they've confirmed this behavior. It forces us to embrace the weirdness of the quantum world.
It's like saying you can be in two different rooms at the same time. How does any of this make sense?
Well, the key is to shift our thinking away from the idea of particles having definite positions and trajectories. In quantum mechanics, we talk about probabilities and wave functions. Instead of saying an electron is here or there, we say it has a certain probability of being in different locations. It's like a cloud of possibilities rather than a pinpoint on a map.
Okay, so instead of thinking of electrons as like tiny balls whizzing around, we should picture them as more like fuzzy clouds of possibilities. I can kind of see how that might explain how they can be in multiple places at once. But how does this apply to the structure of atoms? We learned about electrons orbiting the nucleus in neat little paths. Is that all wrong?
It needs some refining for sure. Those neat little orbital paths, those are a simplification. In reality, electrons, they exist as a cloud of probability around the nucleus. They don't follow specific paths like planets orbiting a star. Instead, they're spread out with a certain probability of being found in different regions.
So it's more like a fuzzy cloud surrounding the nucleus than a miniature solar system. Does this have anything to do with that Heisenberg uncertainty principle I've heard about, the one that says you can't know both the position and momentum of a particle with perfect accuracy?
You got it. The uncertainty principle is a fundamental consequence of wave-particle duality because particles have wave-like properties. Their position and momentum are inherently fuzzy. The more precisely you try to measure one, the less precisely you can know the other.
So it's not just a limitation of our measuring tools. It's a fundamental property of the quantum world itself. We can't know everything about a particle with perfect certainty. That's a pretty profound idea.
Yeah.
But how does this quantum weirdness impact our understanding of the universe on a larger scale? General relativity seems to work pretty well for describing gravity and the large scale structure of the cosmos.
It does. And for most everyday purposes, we don't need to worry about the strangeness of quantum mechanics. But there are places where general relativity breaks down, points where our understanding of gravity hits a wall.
You mean places like black holes? We talked about those earlier.
Yeah.
And how they warp space-time so much that even light can't escape. Are you saying that to fully understand black holes, we need to bring quantum mechanics into the picture?
Exactly. Black holes, they're the ultimate cosmic laboratories for studying the interplay between gravity and quantum mechanics. They represent a point where the immense gravity of a collapsed star creates conditions so extreme that our classical understanding of physics just doesn't cut it anymore. So we need a theory of quantum gravity to truly understand what's going on inside a black hole. But didn't Hawking say that even a unified theory might not be enough to save us from ourselves? Are we doomed to be destroyed by our own scientific progress?
Hawking did express that concern, but he also maintained a sense of optimism. Remember, he believed in the power of human curiosity, that our innate desire to understand the universe will ultimately guide us towards a better future. And that journey of discovery requires us to understand the fundamental building blocks of matter and the forces that govern their interactions.
Right. He talks about these things called elementary particles, quarks, electrons, and all those other subatomic particles that make up everything around us. And then there are these force-carrying particles that mediate the fundamental forces of nature. Photons for electromagnetism, gluons for the strong force, and so on. It's a whole new level of reality, isn't it?
It is, and understanding these particles and forces, it's crucial for piecing together the puzzle of the universe. We need to know not only what these particles are, but how they interact with each other. That's where the concept of quantum fields comes into play.
Quantum fields. What are those? Are they like force fields in science fiction movies?
Not quite. Imagine a field that permeates all of space. A bit like an electric field, but instead of carrying electrical energy, these quantum fields they carry the potential for particles to pop in and out of existence.
Like particles can just appear and disappear. How is that? I mean, how is that possible?
It's one of the most mind-boggling aspects of quantum mechanics. Particles, they aren't these solid permanent things like tiny billiard balls. Instead, they're fluctuations in these underlying quantum fields, kind of like ripples on the surface of a pond.
So particles are like ripples in these invisible fields that fill all of space, and the interactions between particles are like ripples interacting with each other.
Exactly, and this picture, it helps us understand how forces work at the quantum level. For example, the electromagnetic force, which holds atoms together, that's mediated by the exchange of photons, which are ripples in the electromagnetic field.
So instead of thinking of forces as like these mysterious actions at a distance, we can picture them as arising from the exchange of particles between these quantum fields. That's a pretty neat way to visualize it. But the book also mentions something about different types of particles, fermions and bosons. What's the difference?
That's a key distinction in particle physics. Fermions, they're the particles that make up matter, like electrons and quarks. Bosons, they're the force carrying particles, like photons and gluons. And one of the key differences between them is their spin.
Spin. Do particles actually spin like tiny tops?
It's not quite like that. Spin is an intrinsic property of particles, a bit like their angular momentum. But unlike the spin of a top, which can be any value, the spin of particles is quantized, meaning it can only take on specific discrete values.
Okay, so spin is like this built-in angular momentum that can only have certain values. But why is that? I mean, why is that important? Does it affect how particles interact with each other?
It does. One of the key consequences of spin is Pauli's exclusion principle, which applies only to fermions.
Pauli's exclusion principle. Remind me what that is.
It states that two identical fermions can't occupy the same quantum state. Imagine it like a rule that prevents two electrons with the same spin from being in the same place at the same time.
So it's like a quantum social distancing rule for electrons.
That's a great way to put it. And this principle, it has profound consequences for the structure of matter. It's what prevents atoms from collapsing, and it's what gives rise to the periodic table of elements. With each element having a unique configuration of electrons.
So Pauli's exclusion principle is kind of like the traffic cop of the quantum world, keeping things organized and preventing everything from clumping together. That's pretty amazing. But what about the unification of forces? We talked about how the electromagnetic and weak forces were successfully unified into the electroweak force. Is there a grand unified theory, a GUT, that merges the electroweak and strong forces into a single force?
There are several proposed GUTs, but none have been experimentally confirmed yet. They're still very much theoretical. The challenge is incorporating gravity into the picture, finding a way to bridge the gap between general relativity and quantum mechanics.
So a theory of quantum gravity is still the holy grail of physics.
It is, and the quest continues. Scientists they're exploring various approaches, from string theory, where particles are replaced by tiny vibrating strings, to loop quantum gravity, which attempts to quantize space-time itself. It's a fascinating area of research that pushes the boundaries of our understanding of the universe.
Oh, it's amazing to think that there are all these different theories vying to explain the fundamental nature of reality. But before we get too lost in those theoretical landscapes, let's come back to those mysterious objects we touched upon earlier. Black holes. They seem to be a place where all these different strands of physics come together.
They are. Black holes, they're like cosmic laboratories for testing our most fundamental theories. They're the most extreme objects in the universe, where gravity reigns supreme and where quantum effects are thought to play a crucial role.
So are we finally ready to tackle the question of what happens if you fall into a black hole?
Let's dive into that abyss in our next part.
All right, we've journeyed from the vast expanse of the universe to the bizarre realm of quantum mechanics, and now let's confront those cosmic behemoths, the black holes. What happens if you fall into one? Is it instant obliteration, or something even weirder?
It's definitely one of the most intriguing questions in physics, and it touches on some of the deepest mysteries of the universe. Black holes, they're regions of space-time where gravity is so strong that nothing, not even light, can escape. They're like cosmic sinkholes, warping the fabric of reality itself.
We talked earlier about the event horizon, the point of no return. Is that where things get really strange?
Exactly. The event horizon is the boundary beyond which escape from the black hole's gravitational pull is impossible. It's like a one-way door in space-time. Once you cross it, there's no coming back.
So what would happen to someone who dared to cross that threshold? Would they be instantly crushed?
Not necessarily instant. The experience would depend on the size of the black hole. For smaller black holes, the tidal forces, the difference in gravitational pull between your head and your feet would be incredibly strong, stretching you out in a process often called spaghettification.
Ouch. Spaghettification doesn't sound like a fun way to go.
No.
But what about larger black holes? Would it be a gentler demise?
For supermassive black holes, the tidal forces at the event horizon might be surprisingly weak. You might not even notice crossing the event horizon. But regardless of the size, once you're inside, you're inevitably drawn towards the singularity at the center of the black hole.
And the singularity is where things get really mind-boggling, right? It's a point of infinite density where all the matter that's fallen into the black hole is compressed into an infinitely small space. Does that even make sense? Does our understanding of physics just break down at that point?
It does seem to defy our current understanding of physics. The singularity is where general relativity, our theory of gravity, breaks down. We need a theory of quantum gravity to describe what happens at such extreme densities.
So black holes are not only cosmic enigmas; they're also pushing us to the limits of our understanding of the universe. But didn't Hawking discover something groundbreaking about black holes? Something about them not being completely black after all.
He did. Hawking's most famous discovery was that black holes actually emit radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, is incredibly faint, but has profound implications.
Wait, so black holes aren't these cosmic vacuum cleaners that just suck everything in? They actually radiate something back out. Yeah. How is that? How is that even possible?
It's a consequence of the uncertainty principle we talked about earlier. Near the event horizon, virtual particle pairs, they're constantly popping in and out of existence. Normally, these particles they annihilate each other almost instantly. But near a black hole, one particle might fall in while the other escapes, carrying away some energy from the black hole.
So black holes are slowly losing energy and mass through this Hawking radiation. Does that mean they eventually evaporate?
Exactly. Over incredibly long time scales, black holes can evaporate completely. But for typical black holes, the evaporation time is far longer than the current age of the universe.
That's fascinating. So even black holes, these seemingly eternal objects, have a finite lifespan. But this whole idea of Hawking radiation, it raises a lot of questions about information and entropy. What happens to the information that falls into a black hole? Is it lost forever?
That's the famous black hole information paradox. According to quantum mechanics, information cannot be destroyed.
Right.
But if black holes evaporate and the information that fell in is gone, that seems to violate a fundamental principle of physics.
So is there a solution to this paradox? Do we know what happens to the information?
There are many proposed solutions, but none have been universally accepted. Some theories they suggest that the information is encoded in the Hawking radiation itself, while others propose that it's stored in some form within the black hole. It's a topic of ongoing research and debate.
It sounds like black holes are not only pushing the boundaries of our understanding of gravity, but also forcing us to rethink our ideas about information and the very nature of reality itself. But before we get too lost in those cosmic puzzles, let's shift gears a bit and talk about something a little more relatable: time, specifically the arrow of time. We all experience time flowing in one direction, from past to future. But why is that? Do the laws of physics dictate this direction?
That's a profound question that has puzzled philosophers and scientists for centuries. The laws of physics themselves, they're mostly time symmetric, meaning they work equally well in both directions of time. But our everyday experience clearly tells us that time has a preferred direction.
So why do we perceive time flowing in only one direction? Why can't we remember the future or unbreak an egg? Is it all just in our heads?
It's not just in our heads. There are several arrows of time, each pointing in the direction of increasing disorder or entropy. One is the the thermodynamic arrow of time, which is based on the second law of thermodynamics, the idea that that entropy always increases in a closed system.
Okay, so entropy is like a measure of disorder, and things tend to get more disordered over time, not more ordered. My desk is a perfect example of that. But how does this relate to our experience of time?
Hawking argues that our psychological arrow of time, our perception of time flowing from past to future, is linked to the thermodynamic arrow of time. Our brains, like all physical systems, are subject to the second law of thermodynamics. We remember the past because it represents a state of lower entropy, while the future is a state of higher entropy.
That's fascinating. So it's our experience of time is tied to the increasing disorder of the universe.
Yeah.
But why is the universe becoming more disordered in the first place? And how does this relate to the expansion of the universe?
That's where Hawking's no boundary proposal comes in. This proposal suggests that the universe began in a very smooth and ordered state. As the universe expanded, more and more states became possible, leading to an increase in entropy.
So the expansion of the universe is driving the increase in entropy, which in turn shapes our perception of time flowing from past to future. It's all interconnected. But could the universe just as easily be contracting, leading to a decrease in entropy and a reversal of the arrow of time?
That's a good question. Hawking he argues that the conditions in a contracting universe would not be suitable for the existence of intelligent beings like us. We rely on the flow of energy from ordered states to disordered states for our survival. Think of eating food, which is a relatively ordered form of energy, and converting it into heat, which is disordered. That process wouldn't work in reverse.
So we exist in an expanding universe with an arrow of time pointing towards increasing disorder, because that's the only kind of universe where we could exist. It's a mind-blowing thought that our very existence is tied to the large-scale structure and evolution of the universe. But speaking of mind-blowing, let's talk about something even wilder. Time travel. Is it really possible? Could we journey through time like we travel through space?
It's a question that has captured our imaginations for centuries, hasn't it? And while the idea might seem purely fictional, it's actually a topic that physicists have seriously considered. One way to potentially achieve time travel is through wormholes.
Wormholes. Those are like shortcuts through space-time, right? I've seen them in science fiction movies. You go in one end and pop out somewhere else in the universe, or even in a different time.
That's the basic idea. Wormholes, they're hypothetical tunnels connecting different regions of space-time. Imagine folding a piece of paper in half and poking a hole through it.
Yeah.
That hole it acts as a shortcut between the two sides of the paper. A wormhole is like that, but in 4 dimensions.
So you could theoretically travel vast distances in an instant, or you even journey through time.
In theory, yes, but there are enormous challenges. First, we don't know if wormholes actually exist, and even if they do, they might be incredibly unstable and difficult to keep open. Hawking mentions that you would need exotic matter with negative energy density to stabilize a wormhole.
Right, and haven't physicists shown that negative energy densities can exist, at least on a very small scale, like in the Casimir effect.
They have. The Casimir effect, it's a strange phenomenon where 2 uncharged, perfectly conducting plates placed very close together, they experience an attractive force. This force is thought to arise from the suppression of certain quantum fluctuations in the vacuum energy between the plates.
So the Casimir effect provides a tantalizing hint that negative energy densities might be possible, which could, in theory, be used to stabilize a wormhole. That's amazing. But if time travel were possible, wouldn't we have met visitors from the future by now? Where are all the time tourists?
That's the famous Fermi paradox. If time travel is possible, why haven't we encountered any time travelers? There are many potential explanations, ranging from the possibility that time travel is simply impossible to the idea that future civilizations might choose not to interfere with our timeline.
I like that last one. It's reassuring to think that even if time travel were possible, future humans would be responsible enough not to mess things up. But let's shift our focus back to the quest for a unified theory of physics. Is there a theory that can explain everything from the tiniest particles to the grandest structures in the universe?
That's the ultimate goal of physics. A theory of everything that can unify all the forces of nature and explain the fundamental nature of reality. It's a quest that has driven scientific inquiry for centuries, and it continues to inspire physicists today.
We talked about general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the subatomic world. Are we any closer to merging these two seemingly incompatible theories?
There are several promising approaches, but the path to unification is far from clear. One leading contender is string theory, which replaces point-like particles with tiny vibrating strings. String theory requires extra spatial dimensions beyond the three we experience, but these extra dimensions are thought to be curled up at incredibly small scales, too small for us to detect.
So string theory proposes that there are like hidden dimensions woven into the fabric of reality. That's a wild idea.
Yeah.
But does it actually work? Does it successfully unify gravity and quantum mechanics?
String theory is still very much a work in progress. It's mathematically complex and lacks experimental verification, but it offers a tantalizing glimpse into the potential for a unified description of the universe.
It's amazing to think that there are all these different theories vying to explain the fundamental nature of reality. It's a testament to the power of human curiosity and our relentless drive to understand the universe we live in. But as we wrap up this deep dive, I'm left with even more questions than answers.
And that's the beauty of science. Every answer leads to new questions, pushing us further along the path of discovery. Hawking, he reminds us that even if we found a complete unified theory, it wouldn't mean the end of science. There would still be the challenge of understanding the initial conditions of the universe and the potential for other universes with different laws of physics.
It's a reminder that the quest for knowledge is never truly over. There's always more to explore, more mysteries to unravel, and that's what makes science so exciting. So keep looking up, keep questioning, and keep exploring the wonders of the universe. Thanks for joining us in this deep dive into Stephen Hawking's brief history of time.
If you enjoy the video, please like and subscribe.